In our last class, we studied about force due to magnetic field. We will continue our discussion about this force. Now we learned that when a charged particle having charge q moving with velocity v enters a magnetic field then it experiences a force. And the magnitude of this force is given by F is QEB sin theta, or F is given by, so here both V and B are vector quantities. F is Q into V cross B, or if I write V cross B, or if I write only the magnitude, F is given by QEB sin theta. But theta is the angle between V and B. We know here theta is the angle between velocity and the magnetic field. Angle between V and B. Now we will discuss different cases, like what happens to the force if theta is 0, theta equal to 90 degree, and what are these cases. Now next we will write force on a charged particle, in uniform magnetic field B First one, the force on a charged particle in uniform magnetic field B. Now if the particle is at rest, that is if V is 0, then force is 0. Therefore I can write force is 0, force on a charged particle in uniform magnetic field B is 0 if it is at rest. That is, if V equal to 0 or F is equal to 0, that is F is equal to 0 when V equal to 0. If the particle is moving, then only we have the force. If it is rest, then the force is 0. I can write here capital F. Now the second case, that is the case when theta equal to 90 degree. If theta is 90 degree, then sin 90 is 1. The force magnitude is QEB, and I can say that this force is a maximum. Therefore force is maximum. The force is maximum if it is moving in the direction, if it is moving in the direction perpendicular to that of magnetic field. Perpendicular to that of magnetic field. That is, F max is QEB, force is maximum. The force is maximum QVB when theta is 0. Not 0, sorry, theta is 90 degree. Force is QAB when theta is 90 degree. That is when the angle between V and B. That means the particle is moving in a direction perpendicular to the magnetic field. Now third case. The force is minimum or 0, minimum or 0 if it is moving in the direction parallel or anti-parallel to that of magnetic field. Now parallel or anti-parallel, that means actually when theta is 0 or 180 degree. You can write F minimum. F minimum equal to 0 when theta is 0, parallel or anti-parallel. The force is 0 if the charge particle is moving along the direction of the magnetic field or in a direction opposite to the direction of the magnetic field. Now I will tell you some more properties of these forces. Let us write the fourth one. This force cannot accelerate the charged particle. That means the force will not change the magnitude of V. It changes, only it can only change the direction of the particle. So I can write the force cannot accelerate. The force cannot accelerate the charged particle. The force cannot accelerate the charged particle. That means, that is, do not change the magnitude of velocity. It cannot change the magnitude of the velocity. Do not change the magnitude of the velocity or kinetic energy of the charged particle, or Ke, that is kinetic energy of the charged particle. Okay. Now this force, because we know the direction of the force, depends upon whether it is positive charge or negative charge. Anyway, it is perpendicular to when we stretch our right hand rule. When we stretch our left hand, we have seen what is the direction of the force. So this force can change the direction of charged particle. So I can write can only change the direction of motion of charged particle. direction of motion of charged particle. Charged particle can change the direction of, can only change the direction of motion of charged particle in magnetic field. Because I can write, because the force F on the charged particle always remains perpendicular to its velocity. So the force is always perpendicular to velocity, so it can change the direction. Now after entering the magnetic field, what will be the path of the charge? Like, because the force it can change the direction. Now, so if the charged particle enters the magnetic field in a such direction such a way that it is perpendicular to the magnetic field, that means if the velocity and the magnetic field are perpendicular to each other, then the charged particle will follow a circular path. This is an important thing. Sixth one, throws the charged particle. So this force throws the charged particle, moving in direction perpendicular to that of magnetic field. Perpendicular to that of magnetic field in a circular path, such that it provides the required centripetal force. So the first force is equal to the centripetal force. Therefore the radius of the circle is, we can derive this. Now the force QVB, that is because V and B are perpendicular to each other, and this will be equal to the centripetal force. If radius R of the circular path is R and V is the velocity, then it is given by mv square by R. Therefore radius of circular path will become equal to radius of circular path R is equal to mv by qb. Now v will get cancelled, so we will have 1v here divided by qb, mv divided by qb. Now if the angle between V and B is equal to theta, then what will happen? The last point, I think it is the 7th one. Throws a charged particle moving with velocity v moving with velocity v and making an angle theta with the direction of the magnetic field, making an angle theta with the direction of the magnetic field, with the direction of the magnetic field into a helical path. Helical path of radius, r is equal to mv sin theta divided by qb. Okay. Now if the angle between v and b is some angle theta, then the charged particle will follow a helical path and the radius is given by mv sin theta by qb. Here it is mv by qb, but here mv sin theta by qb. Now that's some of the properties of the force due to the magnetic field on a moving particle.